Hello, hello. Okey, jap. Jap. Kuat sangat. Uh, Ya Allah. Sekejap Bapak malu tu. Korang tunggu jap 10 minit. Aku punya apa? Aku punya mic ni tiba-tiba problem. Hello viewers. Jap. Hello, dia pecah-pecah ke? Sekejap. Dengar tak? Dengar tak? Okay, dengar. Okay. Dengar tak? Dengar tak? Okay. Pecah. Aduh, pecah. Okay, dengar, dengar. Aku dah suruhkan video sound dia. Boleh? Okay. Sekejap, aku share link. Korang dah makan belum? Sorry. Oh, okay, Lokman dah share link. Okay, sekejap. Okay, sekejap. Okay, aku akan share notes. Sekejap. Mana WhatsApp aku? Share notes. Aku tak share lagi kan? Okay. Okay. Oh, saya tahan-tahan dua. Ya Allah. Okay, tak apa. Okay, dah dapat notes belum? Kita start dengan dimensional analysis. Okay. Sekejap aku share kat sikit ni. Tengok. Sikit ni. Oh, tak boleh. Tak boleh. Pause lah. Buka flashy. Okay. So, semua dah dapat dah? Abang Penyu, dengar tak Abang Penyu? Are you there? Okay, okay. Ramai tu macam malu pula aku. Okay. So, okay. So, sekarang ni cuba cakap ada dapat notes tak daripada group? Isi this. Oh, tak ada aircon. Aku terus ajar ni. Ajar chapter mana ni, kita dah chapter 7 chapter 8. Okay. Tak, korang dapat tak notes ni? Cuba cakap. Okay, tak apa. Kita teruskan. Aku punya okay. Ashraf Suhaili. Tak dapat notes ke? Okay, tak apa. Aku dah send note.
Send notes? Send notes? The what?
Okay. Fokus. Dah dapat. Okay, dah dapat. Okay, bagus.
Slime notes.
Okay, so chat ni dia ada lag sikit tau. Okay, so okay. Bismillahirrahmanirrahim. So sekarang ni kita masuk dimensional analysis and modeling. So this is chapter 7. I think I'll be talking English too. Okay, so basically kita kena tahu yang dimension ni ada units and okay, so kita go here first. Okay, this is my red dot. I think this is it. Okay. So dimensions ini just like measure of physical quantity away to the sine number. So there is like five primary dimensions or three primary dimensions that we need to memorize, which is the mass, length, time, temperature, and electric current. So usually we would just be focusing on the mass, length, and time because that is the most frequently used dimensions or primary dimensions in physics. So what we need to do is to memorize what parameters have what dimensions. So the most frequent parameters is force. So force is mass times length over time squared. So we need to memorize ml over t squared. Okay, so just bear that in mind that force is ml over t squared. So now we enter dimensional homogeneity. So what does that mean? It means that the additive term in an equation must have the same dimensions. So this is the first example. I will be giving two examples. For the first one is the total change of energy. You have internal energy, you have kinetic energy, and you also have potential energy. So for energy is force times length, which is ml squared over t squared. Internal energy is, as we learned in thermodynamics last sem, m u2 minus u1. Oh, okay. Okay, so it's u2 minus u1. So u is actually energy over mass. So it still equals to energy, ml squared over t squared. Kinetic energy is 1 over 2 m v2 squared minus v1 squared. This is the kinetic energy of the velocity. So if we like open up the dimensions, expand the dimensions, we'll also get ml squared over t squared. And then finally we have potential energy, which is mg z2 minus z1. So it is m, which is mass, g is length over time squared, which is an acceleration constant, and z is length. So all we compared, they all have the same dimensions. So it is called dimensionally homogeneous. Okay. So now Bernoulli's equation. So Bernoulli's equation is used for fluids because what Bernoulli states that the pressure, static pressure, the dynamic pressure, and the like the height of the head is constant. So P1 is equals to P1 plus rho V squared plus rho GZ equals to P2 like that lah. So it's a constant in one condition. So force is pressure is force over area, rho is mass over volume, v squared is velocity squared, which is length over time squared. Then rho gz is mass over volume, length over time squared, and length. And then when we expand the dimensions, they will get all the same dimensions, which is dimensionally homogeneous. Okay. So moving on to the non-dimensionalization of equations. So there are a lot of terms that we need to like understand. So one of it is non-dimensional equation. What does a non-dimensional equation means? It means that all of the parameters in the equation has has no dimensions. For example, efficiency of a motor. If you are calculating an efficiency, it has no dimensions. So it's actually a dimensional parameter, which is this one, non-dimensional parameters. For example, Reynolds and Fox number, and so on, so on. So we have normalized equation. Normalized equation is when all of the parameters in the equation the same and has the same dimensions, or all of them are non-dimensional. So if one parameter has different dimension with another parameter, it is not normalized. Okay. So we enter the parameters. Parameters is there are three parameters: dimensional variable, non-dimensional variables, and dimensional constant. Dimensional variables is like length, time, speed, anything that has dimensions, meter squared, volume over mass, and then we got banyak lah lagi. And then that's the dimensional. The non-dimensional is like angle of rotation, phi and theta, because the angle of rotations doesn't really bring any dimensions because it is a unit, but it is non-dimension because the angle of rotation is not included in the primary dimensions, so that doesn't count as a dimension. Then we have dimensional constant, which is gravity. Okay, and then other than parameters, we also have pure constants, which is 1 over 2 e and also pi. Okay, so if they ask you what are the advantages of non-dimensionalization and equation, well, number one is number of parameters in the non-dimensionalized equation is less than the original number of parameters. Later on, we will see that the pi for a condition reduces from 7 to 4. Okay, that is one of the advantages. Second is the relationship between key parameters. So, for example, we want to study the relationship between the lift force and also the velocity of the wind. Uh, but we don't know how much proportional is it. So from using non-dimensional equation, we can find the relationship between the velocity and also the force. Okay, a parameter that is already dimensionless become a pi parameter by itself. For example, the angle of rotation. Okay, so this is one of the famous non-dimensional parameters, which is Froude number, Euler number, Strouhal number, and Reynolds number. Okay, so kita masuk sini. So this is what we call dimensional similarity. Why we want dimensional similarity is because we want to complete similarity between a prototype and a model. For example here, I have a 3D model of a car. Hey, aku 3D print hari tu. Style kan? So this car needs to be exactly the same, acts the same as a it needs to be exactly the same as the prototype. So we need to remember the prototype is the ones that is in the real life simulation. The model is the one that we can control the size. So this is a model. Okay. So there are three types of similarities: geometric similarity, dynamic similarity, and kinetic similarity. So what does geometric means? It means it is the same shape. It has the same radius of tire. It has the same length. It has the same width, and so on. The dynamic similarity is when all of the forces on the model is scaled by a constant factor to the corresponding forces in the prototype. So what that means is dynamic is a force acting on the body. So the force acting on the model must be equivalent to the force acting on the prototype. Okay. So for example, the force lift, the drag, the pressure for the model needs to be equivalent for the prototype. And then we have kinetic similarity. What does kinetic means? It means something that moves or the body is in a kinetic motion. So the velocity at any point in the model must be proportional to the velocity in the prototype. For example, how is if the model is stationary or if the model is moving, that is kinetic similarity. Okay. So now we enter what is a non-dimensional parameter. So there are two types of non-dimensional parameters. That is dependent and independent. Okay. So take note. In a condition, there will only be one dependent parameter, and the others will be independent. Okay. The dependent parameter will be the function of all of the independent parameters. Okay, you guys you guys might be thinking, what is independent and what is dependent? Kenapa tak pernah dengar? Okay, so right now, we go to page 2. Let's just ignore the other steps. Okay, so in here, over here, we want to determine the dependent parameter and the independent parameter. The dependent parameter is usually the parameter we want to find, such as, okay, you guys can see here, lift force of a wing, drag force of a body, elevation of a ball after it bounces, and also the shear stress in the flowing fluid. An independent parameter is usually the parameters that we can control, which is density, viscosity, mass, velocity, length, and other constants, such as gravity. So, we should also remember that density and viscosity is a function of temperature. That is the only thing that the parameters is depend on, but it is categorized as an independent parameter because they don't depend on anything. They just depend on how we want to control it. Okay, so those are the two parameters that we need to remember. So the dependent parameter is a function of all of the independent parameters in a condition. So how we want to make the similarity is making the dependent parameter similar to the prototype parameters. So pi 1m is equals to pi 1p. So from there, we can conclude that pi 2m is also equals to pi 2p, pi 3m is also equals to pi 3p. And then there we have it, rem equals to rep, which is this is the uh, this is the this is the Reynolds number for the model, and over here is the prototype. So you guys can determine any variable using the other variable. If you guys want to find usually it will ask us to find the velocity of the model or the velocity of the prototype. Okay, so we just use this. Okay, so now we also experimental testing, modeling, and incomplete similarity. So what happens if your prototype and model isn't similar? Because okay, it is not always possible to match the pi p and also pi m. We need to extrapolate the model test data to obtain full scale predictions. Okay, so why this happens is because the Reynolds number for the prototype is usually much higher than the Reynolds number for the model. And if you go to lab facilities, they have like a limit how far they can go. Like a wind tunnel, you have a maximum velocity for the wind tunnel, but you require much higher velocities for the wind. So that's where this comes in. So, certain variables restricts very big values due to facility limitation, which is the wind tunnel. So, for example, we have a wind tunnel. We want to experiment the submarine, okay, submarine. But the required Vm from the equation here, uh, the required Vm is 429 meters per second. So that is quite impossible for the facility to do. So how we solve it is usually using a bigger wind tunnel. There's four steps. First step is using a bigger wind tunnel. Two, using different fluids from air to water or water to air. If you are using a submarine, you can try using from the water to the to the wind tunnel. We should also pressurize the wind tunnel and also adjust the temperature because the density and viscosity is temperature dependent, and also pressure affects the characteristics of the fluids. And also the number four is run near max speed then extrapolate. What does that mean is that we try to run the model at the maximum speed the facility can do. So from there, we can graph the data and we can assume how the data goes. For example, this one here. Okay. So as you can see here, CD is the drag coefficient. RE is Reynolds number. The higher the RE, the higher the Reynolds number, it will like approach the total constant. So we don't need to do experiments for higher Reynolds number. We just need to do experiment until you can find a trend where it shows that it is approaching constant, and then we can just assume or predict. That's why it says predict, full scale predictions. Okay, so that is from the first page. So is there any questions from the chat? Please put your questions in the chat from the first page. If you are okay, type okay. Okay, thank you, Faris. Okay, so now we're moving on to the second page, which is how to generate the non-dimensional parameters. Uh, so this is what we call method of repeating variables. So there's 6 steps. Okay, so the first step is to list all the parameters in the problem. So I have given an example here in the top right corner. This is a wing. So it has, okay, let's count together. We have the first one is okay with that. So step 2 is list the primary dimensions of each parameter. So from here, from the parameters, we want to list all of the dimensions using the mass times length over time squared. Okay. So we need to jot down all of the parameters. Okay, that's step 2. Moving on to step 3 is to calculate the k, which is the expected number of the pi's that we want to find. Oh, okay. Enable tutup wifi. Okay, ya. Aku rasa dia dah on balik. Okay, wait. Okay, dah okay kan balik kan? Oh shit. Kenapa ni? Sekejap, aku rasa di sini. Discord. Ada bateri. Aku dah charge dah. No. Okay, sekejap eh.